John Goodby, first of all, many congratulations on winning the 2014 AkzoNobel Science Award.
Thank you.
You've won it for your work over years, decades on liquid crystals. First of all, you should tell us, what are liquid crystals?
Right, liquid crystals are an intermediate state of matter between solids and liquids. So they look like liquids, but they're actually not really liquids. So this is a good example of a liquid crystal. This is white and it flows like a liquid.
Yes.
But actually, if it was a real liquid, it would be absolutely clear. The whiteness is due to the liquid crystallinity in it.
And people are familiar with them, of course, even if they may not know always that they're made of liquid crystals, from the ubiquitous displays in any sort of consumer electronics gadget now.
Yes.
How do you go from that white milky liquid to the colours and shapes that you can get on a phone, for example, or a computer display?
Well, basically, inside of this white liquid, the molecules are rod-like.
Yes.
And they have a little dipole in this direction.
Yes.
And when you apply an electric field to them, they move around like this.
Okay.
So to get them to move around, you need a display device. And this is one of the original ones that was made many years ago. And inside of it, the liquid crystal fills the whole of this display.
Yes.
And if you hold it up carefully, you can actually see the electrode pattern. So the electrodes are transparent. So they're made of indium tin oxide.
Yes.
And when you apply the electric field to them, the molecules inside of this do that.
Okay.
And that's how they get from black to white. You put polarizers in front and back, and that's how it goes from black to white. How do you get them colored?
Yes.
Well, that's quite simple. You put in a color filter. So the liquid crystal just switches in front of the color. So the filter's always there. So you have red, green and blue filters, and the liquid crystal just shuts them on and off.
Okay, so now we know what we're talking about. Let's step back in time and talk a bit about the history of liquid crystals. When were they first discovered and exploited?
Liquid crystals were originally discovered in 1888 by people, Austrian and German scientists, yes, when they were looking down microscopes at this odd material they got from carrots. And it was, for the early part of the last century, they were mostly worked on in Germany, and they made lots of new liquid crystals. Then from about 1920 onwards, hardly anything was done, except in Hull University.
Did Hull University even exist then?
Yes. Well, no, it was part of the London College.
Yes.
It was a London college, and it had a head of department called Sir Brynmore Jones, and Sir Brynmore was quite keen to start doing new science, and he paddled around a little bit in liquid crystals. And George Gray appeared as a demonstrator to Hull, and he gave George this project of looking at new liquid crystal things, or do kinetics. And George chose liquid crystals, not kinetics.
Roughly when are we talking about?
We're talking about 1940s to 50s.
Right.
And George studied for his PhD in Hull as an external to London University. And again, liquid crystals remained somewhat of a backwater, moderate interest, until he started working with Reckitt Benckiser, as it is now, Reckitt's company that used to make soap, detergent and all that kind of things. And liquid crystals actually are in the cell membranes of bacteria, and that's what he started on. And in about 1970, there was the big discovery at RCA in America, which was that you could make liquid crystal displays.
And that really raised the profile of the
started the whole thing off. So 1970, 1969-70, the Ministry of Defence, of course, got interested in this because the Minister of State at that time, a man called John Stonehouse, I think.
Oh, the one who disappeared, yes.
The one who walked off into the sea. And we were paying RCA more money than it took to build Concorde in just the shadow mass displays for radar. Gosh. And so at the time, solid state electronics was starting as well, so putting a display with solid state electronics was really exciting. And they needed a chemist.
And was that?
And that was George Gray.
Yes. And when did the young John Goodby step into the story?
2 years after that.
Yes.
George had a contract with the Ministry of Defence. He invented this bottle,
Yes.
this liquid crystal. This is actually a hull material.
Mm.
And that was 1972.
Yes.
And I started doing my PhD in 1974 with George.
And what were you working on then?
I was working partly on those kinds of things, but on new liquid crystals that were investigating how matter really melts from a solid to a liquid. And at that time there were only 3 states of matter, solid, liquid and gas, and liquid crystal is the 4th. But in that time I think we've discovered 50 to 60 new liquid crystal phases. So that's what I started on.
So I think it's time to talk a little bit more chemistry, John. What molecules were you working with at this stage, and how were you improving them?
Well, at the start, the molecules were basically made out of aromatic systems.
Yes.
And they look like this one.
Yes.
And this is a cyanobiphenyl.
Yes.
And its viscosity is high relative to modern materials.
Yes.
And so the device didn't switch as fast as you would like to do video.
Yes.
So this material was actually produced by BDH Chemicals at the time.
Yes.
And it was such an improvement of everything else that was out there in the marketplace that Merck bought out BDH.
This is Merck of Germany.
This is Merck of Germany. And they were also involved in developing liquid crystals, and they used some of this similar kind of technology in this other molecule that I have here. And you can see it's very, very similar, almost the same length.
Yes.
And it has the same dipole in it.
Yes.
But it has this part here is not aromatic anymore. This is cyclohexane.
Okay.
And that makes the viscosity lower.
Yes.
And so this switches a lot faster in a device. Also, the optical properties are better. And so these materials form the basis of the development of modern telephones and the like. And then they ended up further developments of that, and they're now in your televisions.
Okay, now you've mentioned Ministry of Defence, you've mentioned RCA and BDH, then bought by Merck. You've mentioned the academic group at Hull. How did all these interplay, the MOD funding, the industrial funding, the academic work?
At the start, of course, Cyril Hilson was running the operations at the Ministry of Defence at RSRE. And
that's at Malvern.
That's at Malvern, and he needed a chemist, and this is where George Gray appeared on the scene. So he got a contract for George,
Yes.
which I think was about £2,000 in 1972. And within 2 years, they'd invented the materials that are used in the first watches and things like that.
So did they deliberately commercialise them and put them onto the consumer market?
Yes, they actually then decided they were going to manufacture.
Okay.
And the manufacturing was done by BDH Chemicals. So they were going to manufacture large amounts of material.
And that was down on the south coast.
Yes,
Is that just because BDH happened to be there?
It's just because BDH happened to be there. And then they set up a network, a consortium as it's called, between BDH Chemicals, the Ministry of Defence and Hull University. And that consortium lasted nearly 25 years or so.
Okay.
And they still funded it from the Ministry of Defence. And there was support funding from EPSRC as it is now, from the research councils. And when Merck took over BDH, they joined in just the same. So it became a three-way arrangement, this time with Merck, the Ministry of Defence and Hull University, and then later on the Ministry of Defence became Kinetic. And so that's how it all developed.
And what were you doing over this period? Because we don't want to lose sight of your contributions to all of this.
I stayed in Hull for the first 8 years or so.
Yes.
And then I left Hull with encouragement by George Gray to go to America. So I spent 10 years at Bell Laboratories in the States.
And Bell Labs was still a great place then.
Yes, it was. We had 6 Nobel Prize winners on site, and Arno Penzias, the discoverer of the Big Bang, was our boss. And then I came back to the UK after 10 years when George decided to retire.
So at Bell Labs, were you working on liquid crystal displays still?
I was supervisor of the liquid crystal research group, and we used to make materials mostly for the physicists and the engineers within the company.
And then when you came back to take over the group at Hull, how did you then decide to direct the academic work?
Well, when I came back, George was still there, so we overlapped by 2 years, and then George retired off to Merck, oddly enough. And then I took over all the research programs that were running, and the programs were running on new forms of liquid crystal. So there were ferroelectrics, low molar mass ones for displays, which are now in cameras, and there were other ones which were polymers, which we started to develop for pyroelectric detection, again mostly with UK industry networks and also with the Ministry of Defence on board as well.
How long have you been at York?
10 years now.
And what are you working on at the moment?
Still working on liquid crystals.
Of course.
This time, well, I'll just give you one or two examples of what we're working on. We're working on liquid crystals that stay in their place. They show an image without any electric field on them, and therefore they have long lifetime, battery lifetimes. And these are being used for supermarket shelving units and things like this.
How do you achieve that what's the word, stickiness in the molecule, so you don't need the electric charge?
You use different types of liquid crystals. So all the work that I did in my PhD is what we're using now. And so the ones in the bottle that I showed you earlier were called pneumatic liquid crystals. And now we're using smectic liquid crystals, which are considerably more sticky. And so you can use an electric field at one frequency to change the orientation of the liquid crystal, and then switch it backwards at another frequency. And once they've switched, they stay there.
Let's look ahead at the future of liquid crystals and their displays using them. How do you see them progressing in the future, and also up against competition such as organic light-emitting polymers, against new forms of light-emitting diodes and so on? Are they holding their own?
I think the future still looks bright for liquid crystals. The displays are getting bigger. You're seeing the introduction of 4K displays, which means 4,000 pixel resolution. So this is the new cinema displays that are just coming out, and they're 60-something inches size. So they're all developments of engineering and so on, whereas the new research that's going on is going towards switchable holograms, a bit like Star Trek, where I saw one where there was a bicycle being projected and it was spinning around like this, and you went to grab it and there was nothing there at all. Amazing new technologies are coming in the future.
How briefly do you go from liquid crystals to a switchable hologram?
You use liquid crystals from my thesis again. That is, this time is ferroelectric liquid crystals, and they're faster switching than normal pneumatic liquid crystals, 1,000 times as much faster, which means you can do a lot quicker addressing with them. And you can find them at the moment in the viewfinders of cameras. And these are used to project light, so you have banks of them projecting light and switching them all the time. And when you get constructive and destructive interference, you create an image.
How good can the colours be with the right filters and so on with liquid crystals?
The colours are an interesting thing if you put them up against OLED. Because OLED black is very good. So if you have an OLED telephone, then the telephone itself is usually blue letters on black background. The reason it's black background is because it's not working. Whereas the liquid crystal display, such as you get on an iPhone, is usually white. And that's because there's an LED backlight on it that keeps it working all the time. So, but OLEDs have a problem of scale up and actually pixel size. So liquid crystal has an advantage that you can make them smaller and smaller pixels. And of course, provided you can make the filters, the color filters that small, then you've not a problem of actually good colour display. Modern LCD TV, where you have the LEDs backlighting them,
Yes.
they actually switch down the LED backlight to the liquid crystal, so the black on an LCD now is almost as good as an OLED black, because the brightness is being controlled by the LED, which switches a lot faster than the liquid crystal. So, you know, older TVs, the black was sort of, you know, not really there. Modern ones are a lot better.
It sounds as though you think the foreseeable future lies with liquid crystal displays.
At the moment, yes, I think that's where it's going. But I don't think liquid crystal is going to go in totally in that direction anymore.
You've mentioned holograms. Is that the other direction you're thinking of?
There are lots of small projection devices that could be made.
Yes.
So you could put a projection device in your telephone and project it onto a wall. So if you're on the train, you could actually watch a video on your train from your mobile phone. That's a possibility in the long term. But I think that one of the great things about liquid crystals is its ability to be used in all different ways, and because of its origin. OLEDs and polymers and things like that are designed specifically to do a display,
Yes.
whereas liquid crystal is actually a phase of matter, which means that it can do many other things. And one of the other things it does rather well is your body, your cells, all these are made up of liquid crystals. Your DNA is liquid crystal. And one of the few things I see in the future is medical applications of liquid crystals, such as in medical prosthetic devices and things like this, maybe artificial bone, things like that, where you're making liquid crystal polymers, or it may be in the use of drug delivery. There are many liquid crystals now used in that area, and recently in the last 5 years we've started to see liquid crystals being used as the carrier for DNA for using them in gene therapy. And for what I understand from America these days, there are now over 100 clinical trials going on using them as vectors to translate DNA across membranes.
And your own future, John, are you going to carry on working in this field?
Well, I will carry on till the day I retire, I think. But at the moment I'm training other people and trying to bring across these new technologies into the classroom. So students in New York now, they get courses on liquid crystals, and we try to bring it home as to what liquid crystals can do. Students have never seen this before. They've come from school, they use all these technologies and they don't know what they are. And so education remains one of the things that I would like to see me carrying on into the future.
Well, many thanks, John. It's been fascinating to hear about the development of the field and to hear about how some of your early contributions, even during your PhD, have come back into use now in new research projects. So many congratulations again.
Thank you very much.